proofs in mathematics. As the name itself says, in this chapter we are going to learn how to prove a given mathematical statement. Now here you can read this sentence. Proof is made up of several mathematical statements, each of which is logically deduced from a previous statement in the proof, or from a theorem proved earlier, or an axiom, or the hypothesis. So any mathematical statement can be proved by using several other mathematical statements which are true. For example, in chapter triangles we learnt about Pythagoras theorem. So what the Pythagoras theorem says: in a right angled triangle, the square of the hypotenuse is equal to the sum of the square of the other two sides. Okay, if ABC is a right angled triangle whose hypotenuse is AC, then AC square will be equal to AB square plus BC square. So the Pythagoras theorem itself is a statement. Okay, the square of the hypotenuse is equal to the sum of the square of the other two sides. This is a statement. Now we should prove this using several other statements. So if we see the proof, here you can see the proof. One line is drawn perpendicular to AC. Okay, now after drawing here, we can observe that triangle ABD is similar to triangle ABC. Triangle ABD is similar to triangle ABC. Therefore, when they are similar, what we can observe, when two triangles are similar, their sides will be proportional. Okay, therefore AD by AB is equal to AB by AC. So when we cross multiply, we get AD into AC is equal to AB square. Okay, now these two triangles are similar. This itself is a statement. Now AD into AC is equal to AB square. So this is a statement. Now again we can observe that triangle BDC is similar to triangle ABC. So these two are similar. That's why the sides will be proportional. Okay, CD by BC is equal to BC by AC. When we cross multiply, we get CD into AC is equal to BC square. Now these two triangles are similar to one another. This is a statement. Now CD into AC is equal to BC square. This is another statement. We'll mark this as 1 and we'll mark this as 2. So when we add 1 and 2 and when we simplify, we finally get that AC square is equal to AB square plus BC square. That means the square of the hypotenuse is equal to the sum of the square of the other two sides. See how we proved so easily. This was the statement which we were supposed to prove. So we proved using several other statements. Which are those statements? Here, this is one statement. These two triangles are similar. Triangle ABD is similar to triangle ABC. Then again, AD into AC is equal to AB square. This is another statement. Again we proved that BDC is similar to triangle ABC. This is a statement. Now CD into AC is equal to BC square. This is another statement. Using all these statements, we proved the given statement to be true. That is, the square of the hypotenuse is equal to the sum of the square of the other two sides. Coming back here, we just now saw how Pythagoras theorem was proved using several other mathematical statements. Okay, now what is a mathematical statement? Mathematical statement is nothing but a meaningful sentence which is not an order or an exclamation or a question. Okay, for example, here you can see which two teams are playing in the Cricket World Cup final. This is a sentence, but it's in the form of question, so this is not a statement. Now here you can see another sentence: go and finish your homework. So this is an order, therefore this also can't be a statement. Now here you can see another sentence: what a fantastic goal. This is an exclamation, so this also can't be a statement. Okay, statement can be one of the following. It can always be true, or it can always be false, or it can be ambiguous. But in maths, a statement is acceptable only if it is either always true or always false. And ambiguous sentences are not considered as mathematical statements. Here you can see ambiguous sentences are not considered as mathematical statements. Example 1 in this chapter: state whether the following statement are always true, always false, or ambiguous. Justify your answers. The sun orbits the earth, so this is false. So what is true? Actually the earth is orbiting the sun, right? Therefore this sentence is false. they have given the answer also. This statement is always false since astronomers have established that the earth orbits the sun. The next question, vehicles have 4 wheels. So this is ambiguous because we can't say whether the vehicle has 2 wheels, 3 wheels, 4 wheels, 6 wheels. Okay, we can't say exactly. That's why this sentence is ambiguous. So it may be true or it may not be true. That's why this is called ambiguous. The next, the speed of light is approximately 3 into 10 power of 5 kilometers per second. So this is true. The statement is always true as verified by the physicists. So the speed of light is 3 lakhs kilometers per second. 3 lakhs kilometers per second means it is like this, 3 into 10 power of 5 kilometers per second. The last one, a road to Kolkata will be closed from November to March. So this is also ambiguous because we don't know which road is being closed. There will be several roads connecting to Kolkata. So which road is closed, that we are not sure. That's why this is an ambiguous statement. This statement is ambiguous because it is not clear which road is being referred to. The last one, all humans are mortal. So mortal means one who has death. Immortal means one who doesn't die. So all humans will die one day or the other. Therefore all humans are mortals, means all humans will die one day or the other. So this sentence is true. This statement is always true since every human being has to die sometime. Example 2 of this chapter. State whether the following statements are true or false and justify your answers. Answers is already given in the textbook, but let me explain you. All equilateral triangles are isosceles triangles. So this is true. So equilateral triangles means 3 sides of the triangle will be equal. Okay, and in an isosceles triangles 2 sides of the triangles will be equal. Okay, therefore all equilateral triangles are also isosceles triangles. Some isosceles triangles are equilateral. So this is also true because isosceles triangles whose base angles are equal to 60 degree are also equilateral triangles. Therefore some isosceles triangles will be also equilateral triangles, and all isosceles triangles are equilateral triangles. So this is false. Not all isosceles triangles. Some isosceles triangles whose base angles are equal to 60 degree will be equilateral triangles. So this is false. And some rational numbers are integers. So some rational numbers, for example 5 by 1 is a rational number. So 5 by 1 is also equal to 5. 5 is an integer. And what is minus 7 by 1? Minus 7 by 1 is a rational number. Minus 7 by 1 is equal to minus 7. Minus 7 is an integer. Therefore some rational numbers are integers. This is true. And here some rational numbers are not integers. Some rational numbers are not integers. For example 1 by 2. 1 by 2 is a rational number, but 1 by 2 is not an integer. Similarly minus 3 by 5 is a rational number but not an integer. So this is true. Some rational numbers are not integers. Not all integers are rational. So this is false. Each and every integer is a rational number. So what are integers? Positive numbers, negative numbers, and 0 are integers. So take any integer, for example 3. 3 is also written as 3 by 1. 3 by 1 is a rational number. And take minus 9. Minus 9 can be written as minus 9 by 1. Minus 9 by 1 is a rational number. So all integers are rational number. Therefore this statement is false. Okay, between any two rational numbers there is no rational number. So this is also false. Between any two rational numbers there will be infinite rational numbers actually. Okay, so for sub question 4, 5, 6 and 7, you can refer to real numbers. Okay, if you read this chapter, you'll have knowledge to answer all these sub questions from 4 to 7. Example 3. So here if x is less than 4, which of the following statement are true? Justify your answer. So here you can see only third option will be satisfied for any value of x which is less than 4. Example 4. Restate the following statements with appropriate condition so that they become true statements. If the diagonals of a quadrilateral are equal, then it is a rectangle. So quadrilateral is a polygon formed by 4 sides, and a rectangle is also a polygon formed by 4 sides. But in a rectangle, opposite sides are parallel to one another. So even in a parallelogram, opposite sides are parallel to one another. So in place of this quadrilateral, if we replace this quadrilateral word by parallelogram, then this sentence will be true. So we can state that if the diagonals of a parallelogram are equal, then it is a rectangle. The next sub question: a line joining 2 points on 2 sides of a triangle is parallel to the third side. So here instead of 2 points, if we insert 2 midpoints, then it will be correct. The line joining 2 midpoints of 2 sides of a triangle is parallel to the third side. So if you go to chapter triangle, you come across one theorem where one line will divide 2 sides proportionally. Okay, when this line divides these 2 sides proportionally, then this line will be parallel to the third side of the triangle. Or simply, if the line passes through the midpoint of these 2 sides, then this line will be parallel to the third side of the triangle. So third question: root p is irrational for all positive integers p. So irrational number you know, and root p is irrational for all positive integers p. What if p is equal to 4? Root of 4 is 2, but 2 is not an irrational number. Okay, similarly root of 9, if we take p as 9, then root of 9 is equal to 3 is not an irrational number. Okay, so this statement will be true if p is not a perfect square. So the ideal statement would be root p is irrational for all positive integers p, where p is not a perfect square. Okay, p can be anything, but p cannot be numbers like 4, 3, 16. 16 also is a perfect square. Square root of 16 is 4, and also 25 also is a perfect square. So p can be any integer except a perfect square. Okay, so root p is irrational number for all positive integers p, where p is not a perfect square. Okay, all quadratic equations have 2 real roots. The last sub question. So in 10th standard there's a chapter called quadratic equation also. In that one you can see that any quadratic equation will have at most 2 roots, not exactly equal to 2 roots. Quadratic equation will have at most 2 roots. Some quadratic equation will have just only 1 root, and some may not have any root at all. Okay, and the answers are already given. I explained to the best of my understanding. Exercise A 1.1, question number 1. State whether the following statements are always true, always false, or ambiguous. Justify your answers. All mathematics textbooks are interesting. So this is an ambiguous statement because there might be some maths book which are boring also. Okay, and if one person find one book interesting, another person may find the same book to be boring. So it depends upon the taste of the person also. So this is an ambiguous statement. The distance from the earth to the sun is approximately 1.5 into 10 power of 8 kilometers. So this is true. Scientists have already proven this one. All human beings grow old. So this is also true, because everybody will age. Okay, it's a known fact. The journey from Uttarkashi to Harsil is tiring. So this is an ambiguous statement. So by which route the journey is done, by what route, whether bus route, train route, or by aeroplane, this is not known. And some may feel it is tiring, some may not feel that the journey is tiring. So we can't say. Therefore this statement is ambiguous. The last statement, the woman saw an elephant through a pair of binoculars. So this is also an ambiguous statement. So we don't know what this woman actually saw. It could be elephant or something else. So this is an ambiguous statement. Exercise A 1.1, question number 2. State whether the following statements are true or false. Justify your answers. All hexagons are polygons. Some polygons are pentagons. So what is a polygon? Polygon is a figure formed by 3 or more sides. And here I have drawn hexagon. You can see hexagon is a polygon formed by 6 sides, and pentagon also is a polygon formed by 5 sides. Therefore the first sub question, all hexagon or polygons, is true, and some polygons are also pentagons. This is also true. Sub question 3, not all even numbers are divisible by 2. So even numbers are 2, 4, 6, 8 and so on. Okay, so each and every number is divisible by 2. Therefore the statement that not all even numbers are divisible by 2, this is a false statement. Sub question 4, some real numbers are irrational. Sub question 5 is not all real numbers are rational. So here you can see I have shown the relation among real numbers, rational numbers and irrational numbers. Okay, Z is the real number, Q is the rational number, and P is the irrational number. So Q means rational number. So rational number is in the form of P by Q, where both P and Q are integers and Q not equal to 0, and the decimal expansion of rational number is terminating or it is recurring. Okay, for example 1 by 2, if you take the decimal expansion of 1 by 2, it is 0.5. Okay, but if you take the decimal expansion of irrational number, it is not terminating and it is not even recurring. Okay, examples of irrational numbers are root 2, root 3, root 5, 2 plus root 3. All these are all examples of irrational numbers. Okay, and a real number consists of both rational number and irrational numbers. Okay, therefore the statement that some real numbers are irrational is true. Okay, and not all real numbers are rational. This is also true. Okay, because real number consists of both rational numbers and irrational numbers. Exercise A 1.1, question number 3, let A and B be real numbers such that A into B is not equal to 0. Then which of the following statements are true? Justify your answers. Both A and B must be 0. Both A and B must be non-zero. Either A or B must be non-zero. So here in the question they are given that both A and B are real numbers and the product of those two real numbers is not equal to 0. Okay, this is possible only when both A and B are non-zeros. Okay, therefore the second option is true. Okay, this option is true. In A and B, if any one is 0, then A into B becomes 0. That's why first option and third option becomes false statement. Exercise A 1.1, question number 4, restate the following statements with appropriate condition. so that they become true. If a square is greater than b square, then a is greater than b. Suppose if I take a as minus 3 and b as 2, then minus 3 the whole square is definitely greater than 2 the whole square. Minus 3 the whole square is plus 10 and 2 the whole square is 4. Therefore 9 is greater than 4. But minus 3 itself is not greater than 2, which is false. Therefore to correct the given statement, a should be greater than 0. Okay, so I can correct the given statement and write as, if a square is greater than b square and a is greater than 0, then a is greater than b. Second sub question, if x square is equal to y square, then x is equal to y. Suppose if I take x as minus 2, so minus 2 the whole square, and if I take y as 2 plus 2, so 2 the whole square, so minus 2 the whole square is equal to 4, and 2 the whole square is also is equal to 4. Okay, now x is equal to y, so minus 2 is minus 2 equal to 2? No, minus 2 is not equal to 2, right? Similarly, if I take x as 3 and y if I take as minus 3, so 2 the whole square, 3 the whole square is 9, and minus 3 the whole square also is 9. But is 3 equal to minus 3? No, 3 is not equal to minus 3, right? Therefore, how can I correct the given statement? So x square, if x square is equal to y square and both x is greater than 0 and y greater than 0, then only x is equal to y. Okay. Sub question 3, if x plus y the whole square is equal to x square plus y square, then x is equal to 0. So here given that x plus y the whole square is equal to x square plus y square, right? So x plus y the whole square, if we expand this, it becomes x square plus y square plus 2xy is equal to x square plus y square. Now here x square terms will get cancelled, y square terms also will get cancelled. So in the left hand side I will be left with 2xy is equal to 0. Now xy, if I bring 2 to the right hand side, it becomes 0 by 2. So xy is equal to 0 by 2 is 0 only. Now here if x is equal to 0, y should be of some value. Okay, y cannot be 0, because if y is 0, we get 0 into 0 is equal to 0, which is not possible. So 0, we can't equate 0 to 0. That's why for x to be 0, y should have some value, whether positive or negative. Okay, therefore I can rewrite the given statement as, if x plus y the whole square is equal to x square plus y square, okay, and y not equal to 0, then x is equal to 0. Fourth sub question, the diagonals of a quadrilateral bisect each other. So what is a quadrilateral? It's a figure formed by four sides. Okay, now consider this quadrilateral. So this is a quadrilateral. Okay, four sides are there. So these are the diagonals. Okay, now I'll name this A, B, C, D, and this is O. So if I say the diagonals bisects, means then AO should be equal to OC and BO should be equal to OD. So this is not possible in all the quadrilateral. Okay, but in case of parallelogram, okay, not even parallelogram, in case of rectangle, in case of rectangle and a square, the diagonals will bisect each other. Now I will draw a rectangle. You can see A, B, C, D, and this is the diagonal So in case of a rectangle, the diagonal bisect each other, and AO will be equal to OC and BO will be equal to OD. Therefore, I can rewrite this statement as the diagonals of a rectangle bisect each other. Will it bisect in parallelogram? Okay, let us see. Yeah, actually in parallelogram also it bisects. Okay, A, B, C, D. So the diagonals of a parallelogram. Okay, in parallelogram and in rectangle also the diagonals will bisect each other. Even in a square the diagonals will bisect each other. Okay, so in place of this word quadrilateral you can use parallelogram, rectangle or a square. And if you see the answer in the textbook, okay, it's given as the diagonal of a parallelogram bisect each other. Okay, but according to me it can be parallelogram, rectangle or a square also. And that completes this exercise. Here you can note one thing: all squares are quadrilaterals, and all rectangles are also quadrilaterals, and all parallelograms are also quadrilaterals, and even squares and rectangles, they are also parallelograms, but not all quadrilaterals are parallelograms, and not all parallelograms are rectangles, and not all parallelogram are squares. The next topic in this chapter is deductive reasoning. So given a mathematical statement, we do proper reasoning on that statement and we'll come to a conclusion. Okay, step by step we'll do reasoning and we'll come to a conclusion, and that's why this is called as deductive reasoning. Okay, and mathematical statements, they are also called as premises or hypothesis. Example 5: given that Bijapur is in the state of Karnataka and suppose Shabana lives in Bijapur, in which state does Shabana live? So here there is two statement or hypothesis or premises, whatever you may call it. The two hypotheses are Bijapur is in the state of Karnataka, Bijapur is in the state of Karnataka. This is one hypothesis or premises. And another hypothesis is Shabana lives in Bijapur, Shabana lives in Bijapur. These are the two premises or the hypothesis. Now from these two hypotheses we can conclude that Shabana lives in the state of Karnataka. Example 6: given that all mathematics textbooks are interesting, and suppose you are reading a mathematics textbook, what can we conclude about the textbook you are reading? So here there are two hypotheses. What are those two hypotheses? All mathematics textbooks are interesting. This is the first hypothesis. Second hypothesis is you are reading a mathematics textbook. Now what is the conclusion? Now our conclusion is that the textbook which we are reading is interesting. Okay, using the two premises or the hypothesis we can deduce that you are reading a interesting textbook. Example 7: given that y is equal to minus 6x plus 5 and suppose x is equal to 3, what is y? So it's a simple problem. See, the two statement or the premises or the hypothesis are: the first hypothesis is y is equal to minus 6x plus 5. The second hypothesis or statement is x is equal to 3. So what is y? It's very simple. You put x is equal to 3 in this y, we get minus 13. Therefore our conclusion is that y is minus 13. Example 8: given that ABCD is a parallelogram and suppose AD is 5 centimeter and AB is 7 centimeter. Okay, see figure A 1.1. What can you conclude about the length of DC and BC? What is the length of DC and BC? So this is also very simple. What are the statements or the hypothesis or the premises given? The first premises is ABCD is a parallelogram. Okay. The second premises is AD is equal to 5 centimeter. This AD is 5 centimeter. The third premises is AB is 7 centimeter. AB is 7 centimeter. So what is the length of BC now? So we know that in a parallelogram opposite sides are parallel and also equal in length. Therefore, if AD is 5, what is BC? BC also is 5. So our conclusion is BC is 5. And what is the length of DC? So in the premises it is given that the length of AB is 7 centimeter. Therefore our conclusion is that CD is also of length 7 centimeter. Okay, it's a very simple problem. Example 9. Given that root P is irrational for all primes P and suppose 19423 is a prime, what can you conclude about square root of 19423? So here there are two hypotheses given, that is root P is irrational for all primes P. That means if P is a prime number, then square root of P is an irrational number, they are telling. Okay. And the second hypothesis is that 19423 is a prime number. So what's our conclusion about square root of 1943? So we can conclude that 1943 is an irrational number. Okay. Now here there is one catch here. Okay. We don't know whether 19423 is a prime number or not. We are not checking. Just going by the statement, we are coming to the conclusion that square root of 19423 is an irrational number. Okay. And suppose if the premises itself is wrong, and our conclusion also will be wrong. Okay. That you can see in the last sentence here. If we start with an incorrect premises, we may arrive at a wrong conclusion also. Okay. Exercise A 1.2, question number 1. Given all women are mortal and suppose A is a woman, what can we conclude about A? So in this question there are two premises. So the two premises are all women are mortal, and the second premises is that A is a woman. Okay. What's the conclusion about A? So from the above two premises we can conclude that A is mortal. Okay. Exercise A 1.2. Given that the product of two rational numbers are rational numbers and suppose A and B are rationals, what can you conclude about AB? So what are the premises given? Premises or the hypothesis or the statement. What are those? Product of two rational number is rational. Okay. And A and B are rational number. So from the above two premises we can conclude that AB is a rational number. Exercise A 1.2. Given that the decimal expansion of irrational numbers is non-terminating and non-recurring, and root 17 is an irrational number. What can we conclude about the decimal expansion of square root of 17? So the hypothesis given in this problem are, okay, first one, decimal expansion of irrational number is non-terminating and non-recurring. Okay, and the second hypothesis is root 17 is irrational number. So we can conclude that root 17, okay, we can conclude that the decimal expansion of root 17 is non-terminating and non-recurring. Okay. Exercise A 1.2, question number 4. Given that y is equal to x square plus 6 and x is equal to minus 1, what can we conclude about the value of y? So what are the hypotheses given in this question? First one is y is equal to x square plus 6, and the second hypothesis given is that x is equal to minus 1. What can we conclude about the value of y? So now y is equal to x square plus 6, right? Put x is equal to minus 1. Okay, when x is equal to minus 1, y is equal to minus 1 the whole square plus 6. So y is equal to minus 1 the whole square is plus 1 plus 6. So y is equal to 7. So the value of y is equal to 7. So here we can avoid writing sentence like we can conclude that the value of y is equal to 7. That we can avoid. We can make it as simple as possible. Okay. Exercise A 1.2, question number 5. Given that ABCD is a parallelogram and angle B is equal to 180 degree, what can you conclude about the other angles of the parallelogram? So hypothesis in this question is ABCD is a parallelogram, okay, and second hypothesis is angle B is equal to 80 degree. What can you conclude about the other angles of the parallelogram? So that means what is angle A, what is angle C, and what is angle D is the question. So A, B, C, D is the parallelogram. A, B, C, D, and angle B is 80 degree. Okay. What are the remaining angles? Now what is angle D? Angle D also is equal to 80 degree because angle B and angle D are vertically opposite angles. In a parallelogram, vertically opposite angles are equal. Okay. So angle D is equal to angle B is equal to 80 degree. So vertically opposite angle. Vertically opposite angles. So vertically opposite angles in a parallelogram are equal. Okay. And what is angle C? Now angle B plus angle C is equal to 180 degree. So these two are supplementary angles. Okay. So supplementary angles. So in an parallelogram, adjacent angles are supplementary angles. Therefore now angle B it is given as 80 degree. So 80 degree plus angle C is equal to 180 degree. Therefore angle C is equal to 180 degree minus 80 degree. If I bring this 80 to the right hand side, so therefore angle C is equal to 180 degree minus 80 degree is 100 degree. So angle C is 100 degree. Now what is angle A? Angle A is equal to angle C, which is equal to 100 degree. Again here vertically opposite angles. Okay, and that completes this problem. Exercise A 1.2, question number 6. Given that PQRS is a cyclic quadrilateral and also its diagonal bisect each other, what can you conclude about the quadrilateral? So the given hypothesis are PQRS is a cyclic quadrilateral. So cyclic quadrilateral means all the vertices of the quadrilateral lies on the circumference of the circle. So here there is some error. My electronic notepad it has some tolerance, that's why I am not able to draw it properly. In my notepad it is looking perfect, but here on the screen here there is some error. Okay, please bear with this. And the second hypothesis is diagonals bisect each other. So diagonals bisect each other means, suppose if the intersection of these two diagonals is O, so diagonals bisect each other means now PO length PO is equal to length OR, and also the length SO is equal to length OQ. That's the meaning of two lines bisecting. Okay, here diagonals are bisecting. Okay, now in any circle the diameters bisect each other. Okay, bisect each other. Okay, take any circle and draw any two diameter, they will bisect one another. Okay, therefore SQ and PQ are diameters. Okay, SP and PQ are diameters, and hence SQ will be equal to PQ, right? Okay, in any circle diameters are of equal length. Okay, therefore SP is equal to PQ. Okay, so in a rectangle also the diagonals are of equal length. Okay, in any rectangle the diagonals are of equal length. Okay, therefore what is our conclusion? Therefore PQRS is a rectangle. Okay, actually PQRS can be a square also. Okay, in your textbook if we see the answer, they have given that to be a rectangle only. PQR is a rectangle they have given. Okay, according to me the answer can be a square also. Okay, and that completes this problem. Exercise A 1.2, question number 7. Given that square root of p is irrational for all primes p, and also suppose that 3721 is a prime number, can you conclude that square root of 3721 is an irrational number? So first we'll write what are the premises. The first premises is square root of p is irrational for all primes p. Okay, the second premises or the hypothesis or the statement is that 3721 is a prime number. Okay, so from these two premises we can conclude that, okay, we can conclude that square root of 3721 is an irrational number. From the above premises. Okay, so we take that the premises is true. Okay, we take that square root of p, square root of a prime number is irrational number, and also 3721 is a prime number, and that's why we conclude that square root of 3721 is a irrational number. Now the question is still continuing. Is your conclusion correct? We don't know. Just going by the premises we concluded, but is it correct or not, they are asking. To check whether our conclusion is wrong or right, we should find the square root of 3721. So let us find it. So we'll group into digits. Now 6 6 are 36. So 37 minus 6 is 1. So add this 6 here. 6 plus 6 is 12. Now take these 2 digits down. So 21. So it is 1 to 1 now. Now 121 into 1 is 121. I'll get 0. Therefore square root of 3721 is square root of 3721 is 61. So that means what? So it means It means 3721 is not a prime number. Okay, is not a prime number. Okay, therefore our conclusion in 1, I'll mark this as 1. So therefore our conclusion in 1 is wrong. Okay, why our conclusion was wrong? Because the premises itself was wrong. What was the premises? In the second premises we can see that it is given that 3721 is a prime number. Okay, the premises itself is wrong. That's why we got our conclusion also to be wrong. So, but when we verified, we found that 3721 is not a prime number at all. Okay. Actually, square root of a prime number will be an irrational number. But here, what we are getting? We are getting a integer. We are getting a whole number. Okay. That's why 3721 is not a prime number. Okay. The last sentence I'll write. Our conclusion in 1 was wrong because the premises or the hypothesis was wrong. In deductive reasoning, we just assume that the given statement or the hypothesis or the premises is true, and we go for the conclusion. Okay, but if the premises itself is wrong, then our conclusion also will be wrong. The next topic in this chapter is conjecture, theorem, proofs and mathematical reasoning. So here you can see one example. There is a circle and there is a point here. So for one point there is only one region. Suppose if there are 2 points and after joining these 2 points we get 2 regions, and if there are 3 points on this circle and after joining we get 4 regions. If there are 4 points we get 8 regions, and after tabulating the number of points and the number of regions like this, okay, can we guess what is the number of regions? Okay, so yes, definitely we can guess. So the number of region is given by this formula 2 to the power of n minus 1. We can check it when n is equal to 1. 2 to the power of 1 minus 1, 2 to the power of 1 minus 1 is 2 to the power of 0, 2 to the power of 0 is 1. Okay, when n is equal to 2, we get 2 to the power of 2 minus 1, 2 to the power of 2 minus 1 is 2 to the power of 1, 2 to the power of 1 is 2, so n is 2. Similarly, when there are 3 points, that means n is equal to 3. So when n is equal to 3, 2 to the power of 3 minus 1, 2 to the power of 3 minus 1 is 2 to the power of 2, 2 to the power of 2 is 4. We get like this. Similarly, when n is equal to 4, we get 2 to the power of 4 minus 1, 2 to the power of 4 minus 1 is 2 to the power of 3, 2 to the power of 3 is 8. So seeing this data, we can guess that the number of region is given by this formula 2 to the power of n minus 1. So this kind of guess is called as conjecture. Okay, here you can see this intelligent guess is called a conjecture. So can we state that the number of region is given by 2 to the power of n minus 1? So that will be a statement. Okay, the number of region is equal to 2 to the power of n minus 1. But this statement, is it true for all values of n? That's the question. Okay, for n is equal to 1, 2, 3, 4 we already checked. For n is equal to 5 also this statement is correct. But actually for n is equal to 6 this statement is wrong. The number of region is given by 2 to the power of n minus 1. This statement is wrong. For n is equal to 6. You can verify. Okay, here they've explained it. Okay, so even one counter example is enough to make a statement false. You can read it here. To disprove a statement, it is enough to come up with a single counter example. What is that counter example here? So for n is equal to 6, this formula doesn't hold good. There is another example in the textbook. So here you can see the sum of the series 1 plus 2 plus 3 up till n terms is given by the formula n into n plus 1 by 2. So this itself is a statement. You have studied this in arithmetic progression chapter. Okay, so this statement should be true for all values of n. Okay, maybe for some values of n this statement is false. Okay, until then we'll assume that this statement is true. Next in the textbook you can see a theorem. So here in this example you can see there is a circle, and from an external point P 2 tangents are drawn, that is PQ and PR. We should prove that these 2 tangents are equal in length. So this one we have already learnt in chapter circle. So in chapter circle there is a theorem which states that length of the tangents drawn from an external point to a circle are equal. So this is a circle, this is external point, 2 tangents are drawn. So how do we prove it? It's very simple. So we'll join this external point with the center. Okay, then we'll join OQ and OR. Now OQ is, what is OQ? OQ is radius and OR also is the radius. Okay, therefore OQ is equal to OR, radius of the same circle. So this is a statement, OQ is equal to OR. Now next, PO is equal to PO. Okay, now in these 2 triangles, there are 2 triangles here formed. In these 2 triangles, side PO is common to both. Okay, OP is equal to OP, common side. Okay, and tangent always makes an angle with tangent always makes an angle of 90 degree with the radius, right? Therefore angle Q will be equal to 90 degree, and similarly and angle R also will be equal to 90 degree. Okay, so this side is equal to this side, and this side is common, and this angle is equal to this angle. Therefore this triangle and this triangle are congruent to one another. Here you can see triangle OQP is congruent to triangle ORP according to right angle hypotenuse side criteria of congruency of two triangles. Okay, therefore if two triangles are congruent, then the corresponding sides will be equal. Therefore PQ will be equal to PR. PQ is equal to PR. See, like this, using so many statements, mathematical statements, we proved that PQ is equal to PR. This is how we are going to prove any theorem. Now coming back to the textbook, you can see there's another example. We should prove that the sum of two rational numbers is a rational number. By deductive reasoning we should prove. So what is deductive reasoning? We'll make a statement which is true, and after that we'll make another statement which is true. So each and every statement that we make will be based on the previous statement. Okay, and finally we can prove it. Now let us see how we can prove this one. So let x and y be rational numbers. So rational numbers means which is in the form of p by q, where p and q both are integers and q not equal to 0. So x they have taken as m by n, where n is not equal to 0, and y they have taken as p by q and q not equal to 0. So when we add x plus y is equal to m plus n plus p plus q we will get. So LCM of n and q is nq. So in the numerator, so here we get m into this q, and here in place here in this one we get this n into p. So mq plus np divided by nq. Now m is an integer, q is an integer, so product of integers is an integer. Here also n is an integer and p also is an integer. Product of two integers is a integer, and again the sum of an integer is an integer. So integer divided by here n and q. N is an integer, q is an integer. So n and q will be an integer. So integer by an integer again. So this will be a rational number. So that's how we can prove. Okay. So therefore x plus y is a rational number. So like this, step by step we'll make statements which are true, and hence we are going to prove it. Okay. Example 7 in the textbook. So prove that every prime number greater than 3 is of the form of 6k plus 1 or 6k plus 5, where k is some integer. So in chapter real numbers you would have learnt about Euclid's division lemma. So according to this theorem, if there are two integers a and b, then there exist unique integers q and r which satisfy a is equal to bq plus r, and r lies between 0 and b. So going by this Euclid division lemma, okay, if p is a prime number, okay, if p is a prime number, and if we divide p by 6, okay, then we get p equal to 6k, or p is equal to 6k plus 1, or p is equal to 6k plus 2, or p is equal to 6k plus 3, or p is equal to 6k plus 4, or p is equal to 6k plus 5. Okay, so where k is a integer. Okay, but if we take this 6k, in this 6k we can write as 2 into 3k. Okay, therefore this is not a prime number. So what are prime numbers? Prime numbers are numbers whose factors are just 1 and itself. Okay, but here in 6k you can see there is a factor, 2 is a factor of 6k. Therefore this is not a prime number. 6k is not a prime number. Similarly 6k plus 2, if we take 6k plus 2, we can take 2 a common factor, 2 into 3k plus 1. Again here there is 2 is a factor. So therefore 6k plus 2 is not a prime number. To be a prime number, the only factors are 1 and itself. Okay, if there is any other number which is a factor, then that number is not a prime number. Again if you take 6k plus 4, this 6k plus 4 if you take, we can take 2 common factor, and left out is 3k plus 1. So again we are getting 2 as a common factor. Therefore 6k plus 4 is not a prime number. again if we take this 6k plus 3, here also we can take 3 as common factor, and we are left with 2k plus 1. So here 3 is a common factor, therefore 6k plus 3 is not a prime number at all. Therefore what is left? Only 6k plus 1, this one, 6k plus 1 is left and 6k plus 5 is left. Therefore 6k plus 1 and 6k plus 5 are the prime numbers. Therefore every prime number greater than 3 is of the form of 6k plus 1 or 6k plus 5 for some integer k. So there is some remarks in this problem. Here you can see, in the above example we have arrived at the conclusion by eliminating the different options. This method is sometimes referred to as proof of exhaustion. So among these options here, we started eliminating one by one. We eliminated 6k. 6k is not a prime number. We eliminated 6k plus 2. This is not a prime number. And again we eliminated 6k plus 4, which is not a prime number. Again we eliminated 6k plus 3, which is not a prime number. And we were left with only 6k plus 1 and 6k plus 5. This is how we proved that the prime number is in the form of 6k plus 1 or 6k plus 5. So whenever we arrive to the conclusion by eliminating like this, then it is called as proof by exhaustion. The next example in this chapter is Converse of Pythagoras theorem. So we need to prove this theorem using deductive reasoning. Okay, so what this theorem says: if in a triangle the square of the length of one side is equal to the sum of the square of the other two sides, then the angle opposite to the first side is the right angle. Okay, so ABC is the triangle in which AC square is equal to AB square plus BC square. Here you can see the hypothesis is that ABC is a triangle where AC square is equal to AB square plus BC square. Now by deductive reasoning I should prove this theorem. So deductive reasoning means I should go on giving statements which are true, and finally I'll be able to prove it. Okay, so here what we'll do is, first we'll make some construction. So we'll draw BD perpendicular to AB. Okay, BD perpendicular to AB, we'll draw such that BD is equal to BC. Such way we'll draw. So construct line BD perpendicular to AB such that BD is equal to BC, and join AD, and also join AD. Now BD is perpendicular to AB, so angle ABD is 90 degree. Therefore this is a right angle triangle. Therefore square of the hypotenuse is equal to sum of the square of the other two sides. That means AD square is equal to AB square plus BD square. You can see here AD square is equal to AB square plus BD square. But BD square is also equal to BC. Therefore in place of BD square I can write BC square. If I write BD square, then AD square is equal to AB square plus BC square. Okay, but from the hypothesis we know that AC square is also equal to AB square plus BC square. That means AD is equal to AC. Okay, so that means AD is equal to AC. Okay, now in these two triangle ABC and ADB, we came to know that AD is equal to AC. Okay, and BD is equal to BC, and AB is common side for both the triangles. Therefore these two triangles are congruent to one another. So if these two triangles are congruent, then the corresponding angles are also equal. Okay, that means angle ABD should be equal to ABC. Okay, see here you can see. So we have just shown that AC is equal to AC, also BC is equal to BD by construction, and AB is common. Therefore by SSS criteria of congruency of triangles, these two triangles, triangle ABC is congruent to triangle ABD. Therefore the corresponding angles are equal. That means angle ABC is equal to angle ABD. Okay, see all these are statements. Okay, all these are statements. Okay, and analysis is, it's not compulsory to write. Okay, just for our understanding they have written. So in exam you can write only these statements and you can prove it, and that completes the exercise the example problems. So here you can see some remark. Each of the result above has been proved by a sequence of steps, all linked together. Their order is important. Each step in the proof follows from previous steps and earlier known results. Okay, so step by step we keep on making statements which are true, and each step is based on the previous step. Okay, we can't mix these steps. Okay, exercise A 1.3, first question. Prove that the sum of two consecutive odd number is divisible by 4. Okay, now any odd number is given by 2n plus 1, where n is some integer. Okay, for example, okay, if I take n is equal to 0, okay, I'll get 2n plus 1 as 2 into 0 plus 1, so I'll get this is equal to 1. For n is equal to 1, I'll get 2 into 1 plus 1, 2 1s are 2 plus 1 3. For n is equal to 2, I'll get 2 into 2 plus 2, sorry 1, so 2 2s are 4 plus 1 5. For n is equal to 3, I'll get 2 into 3 plus 1, 2 3s are 6 plus 1, I'll get 7. So here you can see the list goes on. Okay, so odd number is given by 2n plus 1. So therefore consecutive odd numbers are 2n plus 1. The next number will be 2n plus 3. Okay, if you add 2 to an odd number, it becomes the next odd number. Okay, so 2n plus 1 plus 2 gives 2n plus 3. Okay, therefore consecutive odd numbers are 2n plus 1 and 2n plus 3. Okay, now what's the question? Prove that the sum of consecutive odd numbers is divisible by 4. Okay, we'll add these two. Therefore 2n plus 1 plus 2n plus 3, what do we get? Open the bracket, 2n plus 1 plus 2n plus 3. So here 2n plus 2n, I'll get 4n. 1 plus 3, I'll get 4. Okay, now again I can take 4 as common factor, I'll get n plus 1. So what it means? 2n plus 1 plus 2n plus 3. So what it means is 4 is a factor. Okay, this means 4 is a factor. 4 is a factor of 2n plus 1 plus 2n plus 3. Therefore 2n plus 1 plus 2n plus 3 is divisible by 4. Okay, for example, okay, 8 I can write as 4 into 2. What it means? 4 is a factor of 8. That means 8 is divisible by 4, right? Now 16 I can write as 4 into 8. That means 4 is a factor of 16. That means 16 is divisible by 4. Similarly, take 36. If I take 36, I can write this as 4 into 9. Okay, sorry, this one is, it is 4 4s are 16. Okay, now 4 into 9 is 36. That means 4 is a factor of 36. That means 36 is divisible by 4. So similarly, here 4 is a factor of 2n plus 1 plus 2n plus 3. That means 4 divides 2n plus 1 plus 2n plus 3, and that completes the proof. So all this whatever I've written, so this is one statement, this is one statement, this is one statement, the last one is a statement. Okay, all statement, so each and every statement is supporting the previous statement. Okay, and finally I proved that 4 divides 2n plus 1 plus 2n plus 3. That means 4 divides the sum of any two consecutive odd numbers. Exercise A 1.3, question number 2. Take two consecutive odd numbers, find the sum of their squares and add 6 to the result. Prove that the new number is always divisible by 8. So this is similar to the previous problem number 1. Okay, now any odd number is given by 2n plus 1, where n is any integer. Okay, therefore consecutive odd numbers are 2n plus 1 and 2n plus 3. So what is the problem? Take two consecutive odd numbers, find the sum of their squares. So sum of their squares means 2n plus 1 the whole square plus 2n plus 3 the whole square. What is this? Equal to. So now this is equal to, open the bracket. So use the formula and expand. What is a plus b the whole square? It is a square plus b square plus 2ab. So expand this one. So this is 2m the whole square plus 1 square plus 2 into 2n plus 1. So sorry, 2 into 2n into 1. Okay, plus 2n the whole square plus 3 square plus 2n into 3. So this is equal to 4n square plus 1 square is 1 only. So that is next is 2 into 2 is 4 n into 1 is 1 only. So 4n plus, here again 2n the whole square is 4n square plus 3 square is 9 plus 2 into 2n into 3, or 2 into a into b, right? So okay, it's 2 into, this is 2 into 2n into 3. So that is 2 2s are 4, 4 3s are 12. Okay, that is 12n I will get. So now here 4n square plus 4n square I will get 8n square plus, now 1 plus 9 is 10 plus 4n plus 12n is 16n I will get. So this is 2n plus 1 the whole square plus 2n plus 3 the whole square. Okay, now what's the question? Find the sum of their squares and then add 6 to it. Okay, so we'll add 6 to this one. Now I'll mark this as 1. So now if adding 6 means both the sides I should add 6. Okay, so 2n plus 1 the whole square plus 2n plus 3 the whole square plus 6 is equal to 8n square plus 10 plus 16n plus 6. So I'll get 8n square plus 10 plus 6 is 16 plus 16n I'll get. Now here I can take 8 common factor, 8 as common factor. I am left with n square plus 8 2s are 16 plus 8 2s are 16. So 8 into n square plus 2n I am getting. So 2n plus 1 the whole square plus 2n plus 3 the whole square plus 6 is equal to 8 into n square plus 2 plus 2n. So here what it means? It means 8 is a factor of this. Okay, this means 8 is a factor of 2n plus 1 the whole square plus 2n plus 3 the whole square plus 6. 8 is a factor of this one. Therefore 8 divides 2n plus 1 the whole square plus 2n plus 3 the whole square plus 6. Okay, if you want any another example, I can write 16. So 16 is equal to 8 into 2. So what it means? 8 is a factor of 16. That means 8 divides 16, right? And what is 80? 80 I can write as 8 into 2. Sorry, 8 into 10. So what it means? 8 is a factor of 80. That means 8 divides 80. So here also, applying the same logic here, 8 divides 2n plus 1 the whole square plus 2n plus 3 the whole square plus 6. This problem is similar to the previous problem. Okay, and that completes this problem. So here you can see all step by step. Okay, this is first step, this is the second step, like this, step by step I give statements. All these are statements only, all these are mathematical statements, and finally I proved that 8 divides 2n plus 1 the whole square plus 2n plus 3 the whole square plus 6. Exercise A 1.3, question number 3. If p greater than or equal to 5 is a prime number, show that p square plus 2 is divisible by 3. And they have given the hint also, use example 11. So in example 11 they have used Euclid's division lemma. Okay, see, according to Euclid's division lemma, if a and b are two integers, positive integers, then we can express a is equal to b into q plus r, where q and r are some integers. Okay, that means if I divide a by b, I'll get quotient q and remainder as r. That's the meaning of this. Okay, and r will be always less than b only, less than b and greater than or equal to 0. Okay, now applying Euclid division lemma here, p and 3 are integers, therefore I can express p is equal to 3q plus r, where q is the quotient and r is the remainder, and r is always less than this b, less than 3 and greater than or equal to 0. Okay, therefore possible values of p are, I'll get p is equal to 3q plus 0, or I'll get p is equal to 3q plus 1, or I'll get p is equal to 3q plus 2. Okay, r is between 0 and 3 only. Okay, so if p is equal to 3q plus 0, that means 3 is perfectly dividing p. Okay, if r is equal to 0, then p is not a prime number. Okay, if remainder becomes 0, then 3 divides p. Okay, what are prime numbers? Prime numbers are numbers which are divisible by 1 and itself only. If there is any other number which divides the prime number, then that number, it's not prime number at all. Okay, therefore r cannot be 0. If r is equal to 0, p is not a prime number. So I'll exclude this option. Now I'll come to the second option. P can be 3q plus 1, remainder can be 1. Now what I'll do is, what's the question they've asked? Show that p square plus 2 is divisible by 3. Now I'll take p square plus 2. Okay, p is 3q plus 1, therefore p square is equal to 3. Okay, p square plus 2 is equal to now 3q plus 1 the whole square plus 2. So this is equal to, now expand this one, 3q plus 1 the whole square. So this is a square plus b square plus 2ab, right? The formula of a plus b the whole square is a square plus b square plus 2ab. Okay. Now using this formula expand this. This is 3q the whole square plus 1 square plus 2 into 3q into 1 plus 2. So I'll get this is equal to 9q square. So plus 1 square is 1 plus 2 3s are 6. 6 into 1 is 1. 6 into 1 is 6. So 6q plus 2 I'll get. So I'll get 9q square plus 6q. 1 plus 2 is 3. So this I can write, I can take 3 as common. So 3 if I take common, in the first term I'll be left with 3q square. In the second term I'll be left with 2q. 2 3s are 6, right? And here 1 I'll be left. So now what does this mean? This means 3 is a factor of pq square plus 2. Okay. Therefore 3 is a factor of p square plus 2. Now coming to the last option. So p can also be 3q plus 2. Now if I do p square plus 2, what will I get? So 3q plus 2 the whole square, this is equal plus 2. Okay, this is equal to, expand now, 3q the whole square is 3q the whole square plus 2 the whole square plus 2 into a into b, 2 into 3q into 2 plus 2. Okay, now this is equal to 3q the whole square is 9q square plus 2 square is 4 plus 2 3s are 6, 6 2s are 12, 12q plus 2. So I'm left with 9q square plus, so 12q plus 4 plus 2, this 4 plus this 2 is 6. Now again here I can take 3 common factor. 3, if I take common factor, I'm left with 3q square plus 3 4s are 12, 12q plus 3 2s are 6. So p square plus 2 is equal to 3 into 3q square plus 4q plus 2. So here I am getting 3. So again here also, therefore 3 is a factor of p square plus 2. That means 3 divides p square plus q. Okay, that is 3 divides p square plus 2. Okay, so if this is case 1, this is case 2, this is case 3. So when we divide a prime number, we will never get remainder 0. That's why we won't consider this option, that is case 1. Okay, but if we divide a prime number by 3, we'll get remainder 1 or remainder 2. That one I shown here. This is remainder 1 and here remainder 2 we got. So when we get remainder 1 also, we get p square plus 2. Okay, we get here, when remainder is 1, we get p square plus 2, which is divisible by 3 here. Okay, and again when remainder is 2 also, we get 3, which divides p square plus 2. Okay, therefore whenever p is greater than or equal to 5, which is a prime number, then p square plus 2 is always divisible by 3. Okay. Exercise A 1.3, question number 4. Let x and y be rational number. Show that x and y is a rational number. So what is a rational number? Rational number are numbers which is in the form of p by q, where p and q are integers and q not equal to 0. So I'll take let x is equal to p by q, and y is equal to, I'll take m by n. So and the if x and y are rational numbers, then p, q, m and n are integers. Okay, and q not equal to 0 and n also not equal to 0. So in this case x and y will be rational numbers. Now what is x into y? X into y is pq into mn. Now we can multiply the numerator. P into m is pm and q into n is qn. Okay, now p is an integer, m also is an integer. Therefore, what is integer into integer? Integer into integer. Integer into integer is an integer only. Okay, therefore numerator is an integer. P is integer, m is integer, so pm is integer. Q is integer, n is also integer, so qn also is integer. So now again, by definition, x into xy is integer by integer, which is a rational number. Okay, so xy is integer by integer, and also q into n. Q into n is not equal to 0 because q not equal to 0 and n also not equal to 0. Okay, product of two numbers which are not 0 is not 0. Okay, so q into n is something but not 0. Okay, therefore according to definition of a rational number, xy is a rational number because numerator is an integer, denominator also is an integer, and denominator is not equal to 0. See, I used step by step. This is first step, second step, third step. Okay, all these are statements only. This is one statement, this is one statement, this is one statement, this is one statement. So, and last one is the conclusion. So giving proper mathematical statements which are true, I came to the conclusion that xy is a rational number. This is how we solve using deductive reasoning. Okay, exercise A 1.3, question number 5. If a and b are positive integers, then you know that a is equal to bq plus r and r is less than b and greater than equal to 0, where q is a whole number. Prove that HCF of a comma b is equal to HCF of b comma r. So here given a and b are positive integers. Okay, and a is equal to bq plus r and r is less than b and greater than or equal to 0. Okay, I should prove that HCF of a comma b is equal to HCF of b comma r. So this is the question. So coming to solution. So they have given a hint also. They are told to take HCF of b comma r to be h, so that b is equal to k1 times of h and r is equal to k2 times of h, where k1 and k2 are prime numbers or co-prime numbers. If we consider two prime numbers at a time, then they are called co-prime numbers. Okay, if it is confusing, you can just consider it to be a prime number. Okay, now let HCF of b comma r equal to h. Okay, therefore b is equal to k times of h and r is equal to k2 times of h. Okay, where I'll mark this as 1 and I'll mark this as 2, and both k1 and K2 are prime numbers. Okay, if you want an example, I can give you one example. Now 15 I can write as factors of 15 are 3 and 5, so 3 5s are 15, and factors of 16, so factors of 6 are 2 and 3. Okay, now you can see 3 is the only common factor between 15 and 6. Therefore HCF of 15 comma 6 is equal to 3. Okay, now 15 I can write as 5 into 3, so this is HCF. Okay, and this is K1. Similarly 6 I can write as 2 into 3, so this is H and this is K2. Okay, so now here B is equal to K times of H and R is equal to K2 times of H. Now given A is equal to BQ plus R, this is given. Now I'll substitute B is K times of H and K times of H into Q, plus R is K2 times of H. Okay, how I got this? From 1 and 2, from equation 1 and 2. Okay, now here I can take H common factor, so I am left with K1 times of Q plus K2, so this is equal to A. Now what this implies? This implies that H is a factor of A. This implies that H is a factor of A. Okay, for example 10 I can write 2 into 5, so that means 2 is a factor of 10, also 5 is a factor of 10. So here A is equal to H into K1, A is equal to H into K1 times of Q plus K2, therefore H is a factor of A. Okay, now consider A is equal to H times of K1Q plus K2 and B is equal to, what is B? B is K times of H1, or I can write H into K1. Now H is a common factor between A and B. Okay, and also H is the only highest common factor of A and B, because K1 is a prime number. See, suppose if A was something like this, H into C into D, and if B was H into C, then I could have taken, apart from H, I could have taken C also. Then the HCF would be, HCF of A and B would be H into C. Okay, but here I can't factorize K1, that's why H is the only common factor between A and B. Okay, K1 is a prime number, and prime number cannot be factorized. Okay, prime number cannot be factorized. Example of prime numbers are 2, 5, 7, 11, 13, 17, okay, 23. All these are prime numbers which cannot be factorized. Okay, so H is the only highest common factor of A and B, because K1 is a prime number. Okay, therefore HCF of A comma B is equal to H, and that completes the proof. If you study chapter real numbers, you will come across many questions which are similar to this question. Exercise A 1.3, question number 6. a line parallel to side BC of a triangle ABC intersects AB and AC at D and E respectively. Prove that AD by DB is equal to AE by AC. So the diagram is like this. ABC is a rectangle and a line is drawn parallel to side BC, okay, and this line intersects AB and AC at D and E, okay. That means D is parallel to BC, and I need to prove that AD by DB is equal to AE by AC, okay. Now in the diagram you can see that there are two triangles, okay. In triangle ADE and ABC, okay, these are the two triangles, okay. Angle A is common to both the triangles. Angle A is common, okay. Now since D is parallel to BC, angle D is equal to angle B, okay. Angle D is equal to angle B. So these are corresponding angles, okay. Corresponding angles. Since D is parallel to BC, angle D is equal to angle B, and also we can notice that angle E is equal to angle C. This is also corresponding angles, okay. And okay, I'll write here, and angle A is common, okay. Therefore triangle ADE is similar to triangle ABC according to angle criteria, AA criteria, angle criteria of similarity of two triangles. These two triangles are similar. So therefore if two triangles are similar, then the sides are proportional. That means AD by AB is equal to AE by AC is equal to DE by BC. Now I'll take only these two, okay. That is AD by AB is equal to AE by AC. Now I'll take reciprocal. Taking reciprocal. If I take reciprocal, numerator comes to denominator, denominator comes to numerator. So it becomes AB by AD is equal to AC by AE. Now I'll subtract 1 on both sides. Subtracting 1 on both sides. So I'll get AB by AD minus 1 is equal to AC by AE minus 1. If I subtract 1 on both sides, the value of the equation does not change, okay. Now I can write this as AB by AD minus 1, I can write as 1 by 1. This is equal to AC by AE. Here also 1 I can write 1 by 1. Now in the left hand side, what is the LCM of AD and 1? LCM of AD and 1 is AD, okay. So AB by AD minus LCM becomes 1. Therefore the numerator AD will come. AD by AD is equal to, here also AC by AE minus AE by AE. So here in the denominator of the left hand side it is AD. So in the numerator AB minus AD will be there. This is equal to, here in the denominator AE, AC by AE. Now in the figure you can see what is AB by AB minus AD. AB minus AD is BD, okay, BD by AD. Now AC, again see the diagram, what is AC? AC minus AE. AC minus AE is EC. So EC by AE. Now again I will take reciprocal. Taking reciprocal, So if I take reciprocal, numerator will come to denominator, denominator will come to the numerator. So if I take reciprocal, AD by BD is equal to AE by EC. Okay, this is what I was supposed to prove, and I proved it. Okay, so here in this solution you can see each and every step is a mathematical statement which are true, and each statement is based on the previous statement. Okay, so like this making statement by statement which are true, and finally coming to the conclusion is called as deductive reasoning. Okay, this question number 6. Okay, this is actually a theorem which you may have already studied in chapter triangles. Okay, here you can see if a line is drawn parallel to one side of the triangle to intersect the other two sides in the distinct point, the other two sides are divided in the same ratio. Okay, this is actually a theorem. The next topic in this chapter is negation of a statement. Now consider one statement: it rained in Delhi on 1st September 2005. Now this statement can be represented by a letter P and a colon like this: P colon, it rained in Delhi on 1st September 2005. Similarly, all teachers are female. This is a statement. This can be represented by a letter. In this case, it has been represented by letter Q. Q colon, all teachers are female. Now Mike's dog has a black tail. This is a statement. This has been represented by letter R and a colon like this. So like this, any mathematical statement can be represented by a alphabet and a colon like this. Okay, you can choose any alphabet. That's not an issue. Okay. Now can we give a negative statement for all these statements? Yes, we can give. Okay, it rained in Delhi on 1st September. This is the given statement. So when we negate this statement, that is represented by not P. You can see here, if P is the statement, then the negation of that statement will be not P. Okay, and what will be the negation of this statement is this. Okay, it rained in Delhi on 1st September 2005 is the statement. So it did not rain in Delhi on 1st September 2005 will be the negation of this statement. Okay, now the second statement is all teachers are female. This is represented by Q. So negation of this statement will be not of Q, not Q. Okay, now here you can see not all teachers are female. So this is the negation of this statement, all teachers are female. Okay, the third statement, Mike's dog has a black tail. Okay, this is represented by R colon. So the negation of this statement will be not of R, like this, not of R. So negation of this statement is, here you can see Mike's dog does not have a black tail. This is the negation of that statement. And the fourth statement is 2 plus 2 is equal to 4. So negation of this statement will be not of S, which is 2 plus 2 is not equal to 4. The last statement was triangle ABC is a equilateral triangle. Okay, negation of that will be not of T. So not of T is triangle ABC is not equilateral. Whenever we make a negation of a statement, you should note this point. Okay, if P is the statement and not P is its negation, then not P is false whenever P is true, and not P is true whenever P is false. So keeping this in mind, we should make the negation of a statement. Next is example 12 in the textbook. State the negation for the following statements. Answers already have been given here. I'll be explaining you why such answers have been given. Okay, now first sub question, Mike's dog has a black tail. So if this statement is true, we should make a statement which is false. Okay, Mike's dog does not have a black tail, therefore Mike's dog has a black tail will be the negation of this statement. The second question, all irrational numbers are real numbers. So what are irrational numbers? Examples if we can give is root 2. Root 2 is an irrational number. Root 3 is an irrational number. Root 7 is an irrational number. Then root 3 by 5 is an irrational number. 2 root 2 is an irrational number. 1 plus 2 root 3 is an irrational number. So all irrational numbers are actually real numbers only. So this statement is a true statement. So we can make this statement false by just adding one not here. Okay, not all irrational numbers are real numbers. Okay, now the third example, root 2 is an irrational number. So this is a true statement. So this can be made false by just adding one not here. You can see root 2 is not irrational number. So this is a false statement, this is a true statement. Now coming to the fourth example, some rational numbers are integers. So what are rational numbers? Rational numbers are in the form of p by q, where both p and q are integers and q not equal to 0, right? So now 5 by 1 is a rational number. 5 by 1 is also equal to 5, and 5 is an integer. Similarly, minus 8 by 1 is a rational number, and minus 8 by 1 is also equal to minus 8, and minus 8 is an integer. So there are some rational numbers which are actually integers. So this is a true statement. So false will be no rational number is an integer. Okay, this is a true statement, this is a false statement. So here we are replacing some with no. Okay, now fifth example, not all teachers are males. So if this is a true statement, then all teachers must be males will be the false statement. Okay, so we are eliminating this word not here. Okay, all teachers are males. If this was given, if all teachers are males was the question, this would have been the answer. Not all teachers are males. Okay, so if this is true, this is false. If this is true, then this is false. Okay, now sixth question, some horses are not brown. Okay, so here we'll be replacing some with all. Okay, all horses are brown, and there is no real number x such that x square is equal to minus 1. So this is a true statement. Okay, there is no real number such that square of that real number is equal to minus 1. Therefore the false of this statement would be there is at least one real number x such that x square is equal to minus 1. So this is a false statement, this is a true statement. There are some remarks here. You can see, from the above discussion you may arrive at the following working rule for obtaining the negation of a statement. First, write the statement with a not. For example, in the second sub question you can see all irrational numbers are real numbers. So in the negation of the statement we just added not all. Okay, not all irrational numbers are real numbers. And even in the third example, root 2 is irrational, we just added one word not. Root 2 is not irrational number. Okay, but sometimes there might be some confusion. Okay, you can see here, if there is any confusion, make suitable modification, especially in the statements involving all or some. For example, in the fourth case, you can see in the fourth example, some rational numbers are integers. So can the negative of this statement be some rational numbers are not integers? Okay, some rational numbers are integers and some rational numbers are not integers, both are same only. So that's why instead of using not there, what we did is we replaced some with no. Okay, no rational number is an integer. Okay, now again coming to the sixth example, some horses are not brown. Okay, some horses are not brown is same as some horses are brown, both gives the same meaning. That's why here in place of some we replaced by the word all horses are brown. So whenever there is all and some, you should carefully make the negation of the statement, otherwise you may end up making a statement which is same as the given statement itself. Next is exercise A 1.4. State the negation of the following statements. So answer already I have given here. So I'll be explaining why such answers have been given. So man is mortal. So man is mortal means man has death. Okay, one day man has to die. So this is true for any person. So to make this false, we'll add one word extra, that is not. Okay, man is not mortal is the negation. Next one is line L is parallel to line M. Again here we can negate this statement by adding just a word not. You can see here line L is not parallel to M. We just added one word not. So third one, this chapter has many exercises. So here also we can add one word not, but to make this statement, make the negation of the statement meaningful, we'll add one more word, that is does not. Okay, so this chapter does not have many exercises. Third sub question, all integers are rational numbers. So what are integers? Integers are all positive numbers, negative numbers and 0. Okay, and what are rational numbers? Rational numbers are numbers which can be represented in the form of p by q, where both p and q are integers and q not equal to 0. So any integer is a rational number actually. See, for example, take 5. 5 is an integer. 5 can also be written as 5 by 1. So 5 by 1 is a rational number. Similarly, minus 9 is an integer. So minus 9 by 1 minus 9 I can write as minus 9 by 1 also. So minus 9 by 1 is a rational number. So 0 is an integer. 0 by 10 is 0 only. Again 0 by 10 is a rational number. So all integers are rational number. This is a true statement. So to make this statement negative, there should be at least one integer which is not a rational number. Therefore in the answer I will put not all integers are rational numbers. Okay, so not all integers are rational number means there is at least one integer which is not a rational number, but this is a false statement. There is no integer which is not a rational number. Okay, therefore this is a false statement and the given question is a true statement. Sub question 5, some prime numbers are odd. So some prime numbers are odd and some prime numbers are not odd, both have the same meaning. Okay, and what are the prime numbers which are odd? 3, 5, 7, 11, 13, 17, all these are prime numbers which are odd, and prime number which is even is only 2. 2 is the only prime number which is even. So here some prime numbers are odd. This is a true statement. So in the negation I'll state as all prime numbers are not odd. So that means all prime numbers are even. That's the meaning of this statement, which is a false statement. Okay, therefore this is the negation of the statement some prime numbers are odd. Sub question 6, no student is lazy. So that means all the students are not lazy. Okay, to make this if this statement is true, if none of the students are lazy, then to make this statement false, then there should be at least one student who is lazy, right? So therefore in the answer I'll write some students are lazy. This is the negation. Sub question 7, some cats are not black. Some cats are not black and some cats are black, both have the same meaning. Okay, if some cats are not black, if this statement is true, then all the cats are black will be a false statement. Therefore the negation will be all cats are black. Sub question 8, there is no real number x such that square root of x is equal to minus 1. So this is a true statement actually. There's no real number whose square root is equal to minus 1. So to make this statement false, okay, there should be at least one real number whose square root is equal to minus 1. Therefore the answer will be there is at least one real number x such that square root of x is equal to 1. So this is actually a false statement. Okay, there is no real number whose square root is equal to 1. Therefore there is at least one real number x such that square root of x is equal to 1 is a false statement. Sub question 9, 2 divides the positive integer a. So what's the value of a? We are not bothered about that. So we'll just accept for a moment that 2 divides this integer a. Okay, a can be 4, 8, 16, 32, something like that, or 20 or 40. So whatever it is, for a moment we'll accept that a is some number and 2 divides that a. Therefore the negation of that will be 2 does not divide the positive integer a. 2 does not divide the positive integer a. Sub question 10, integer a and b are co-prime. So we don't know the values of a and b. Okay, for a moment we'll accept that these two numbers are co-prime. So negation of this statement will be integers a and b are not co-prime. So just by adding this word not, we'll get the answer. Integers a and b are not co-prime. Exercise A 1.4. In each of the following questions, there are two statements. State if the second is the negation of the first or not. So answer already I have written. So I will tell you why such answer has been taken. So the first sub question, Mumtaz is hungry, and the negation has been given as Mumtaz is not hungry. So if we consider the first statement to be true, if Mumtaz is really hungry, then Mumtaz is not hungry is a false statement. Okay, and if we check the reverse also, if we consider the second statement to be true, first statement should be false. Okay, if Mumtaz is not hungry is a true statement, then Mumtaz is hungry is a false statement. So both sides we are getting the right answer. Okay, therefore this is a correct answer. Mumtaz is not hungry is the negation of the statement Mumtaz is hungry. Sub question 2, some cats are black. The given answer is some cats are brown. See here, both the statement can be true. Okay, some cats may be black and some cats may be brown. So both may be true and both may be false. It's no guarantee that if one is true and one is false. It's no guarantee. Both may be true and both may be false. So the ideal statement ideal negation of the first statement is all cats are not black. Sub question 3, all elephants are huge. One elephant is not huge. Okay, suppose if we consider the first statement to be true, all elephants are huge. The second statement is a false statement. Actually, one elephant is not huge is a false statement. But if we take the second statement to be true, okay, if one elephant is not huge, if this is a true statement, then all elephant are huge should be a false statement. But in this case it doesn't happen. If one elephant is not huge is a true statement, then all elephants are huge also may be a true statement. Both can't be true. Okay, therefore the ideal answer for the first statement will be not all elephants are huge. So here the answer is no. Sub question 4, the given statement is all fire engines are red, and the given negation is all fire engines are not red. At first instance it appears that the second statement is the negation of the first statement. Okay, suppose let us consider the first statement to be true, all fire engines are red. Okay, then all fire engines are not red may be false. Okay, it may be false. But what about the reverse? Suppose if the second statement is true, if all fire engines are not red, then all fire engines are red may be also true. Okay, both can't be true. If one is true, the other should be false. Okay, so if the second is true, the chances that the first statement also is true. So this is not possible. So the ideal answer would be not all fire engines are red. Sub question 5, no man is a cow, some men are cows. So here you can notice that the first statement is always true. There's no man on this earth who is a cow, right? Okay, to make this statement to be false, there should be at least one man who is a cow. Therefore some men are cows is a false statement and is the negation of the given statement. Here always the first statement is true and the second statement is false. Here there's no question of seeing the second statement to be true and the first statement to be false. The next topic in this chapter is converse of a statement. Now consider two statements. First statement is P, it is raining. The second statement is Q, it is difficult to go on a bicycle. Now if I combine these two statements using the words if and then, I can write it as if it is raining, then it is difficult to go on a bicycle. Now this new statement so formed is called a compound statement. There are many ways to form a compound statement, but most commonly compound statement is formed by joining two statements using the words if and then. And now this compound statement is represented by P implies Q. Now we can write the converse of a compound statement also, okay, and that is denoted by Q implies P. You can see here where I have written, okay. Now the converse of this compound statement will be if it is difficult to go on a bicycle, then it is raining. There are several examples in the textbook. So here you can see, write the converse of the following statements. If Jamila is riding a bicycle, then 17 August falls on Sunday. So the answer will be if 17 August falls on Sunday, then Jamila is riding a bicycle. So second sub question, if 17 August is a Sunday, then Jamila is riding a bicycle. If Jamila is riding a bicycle, then 17 August is a Sunday. So actually here sub question 1 and sub question 2 are converse of one another. So this is the converse of this sentence and this is the converse of this sentence. The third sub question, if Pauline is angry, then her face turns red. So the answer will be if Pauline's face turns red, then Pauline is angry. Fourth sub question, if a person has a degree in education, then she is allowed to teach. Okay, if a person is allowed to teach, then that person has a degree in education. If a person has a viral infection, then he runs a high temperature. If a person runs a high temperature, then that person has a viral infection. If Ahmad is in Mumbai, then he is in India. If Ahmad is in India, then Ahmad is in Mumbai. If triangle ABC is equilateral, then all its interior angles are equal. If in triangle ABC all its interior angles are equal, then the triangle is equilateral. If x is an irrational number, then the decimal expansion of x is terminating non-recurring. If the decimal expansion of x is non-terminating non-recurring, then x is an irrational number. If x is a factor of the polynomial p of x, then p of a is equal to 0. So the answer will be if p of a is equal to 0, then x minus a is a factor of the polynomial p of x. So the answers all are given here. The given statements may be true or false, and even the converse of the statement also may be true or false. We are not bothered about that. For example, here you can see if Ahmad is in Mumbai, then he is in India. So this will be a true statement. So whenever this person Ahmad is in Mumbai, that means he is in India. But the converse need not be true always. So what will be the converse of this statement? If Ahmad is in India, then Ahmad is in Mumbai. That will be the converse. But the converse statement may not be true. Okay. Ahmad may be in Bangalore or he may be in Delhi. Okay. So the converse of the statement, if Ahmad is in India, then Ahmad is in Mumbai, may be true or false. So we are not bothered about that. We need to just state the converse of the statement. Next is example 14 from the textbook. State the converse of the following statements. In each case also decide whether the converse is true or false. If n is an integer, then 2n plus 1 is an odd integer. So the converse of this statement will be if 2n plus 1 is an odd integer, then n is an even integer. So the converse will be false. You can see here. Okay, this statement is false because suppose if 2n plus 1 is equal to 15, then we get n equal to 7. But n is not an even, n is an odd number. Therefore, the converse is false. Even I have given one example. You can see, if I equate 2n plus 1 is equal to 7, I'll get n is equal to 3. So n is an odd number. Okay. Therefore, the converse of the statement, if 2n plus 1 is an odd integer, then n is an even integer, is a false statement. Subquestion 2. If the decimal expansion of a real number is terminating, then the number is a rational number. So what is the rational number? Rational number is in the form of p by q, where both p and q are integers and q not equal to 0. So this statement is true actually. Whenever the decimal expansion of a real number is terminating, then it is rational number. So the converse will be, if a real number is a rational number, then its decimal expansion is terminating. So this statement is false. For example, you can see 10 by 3. 10 by 3 is a rational number. So 10 is an integer, 3 is an integer, and 3 is not equal to 0. Okay, denominator not equal to 0, but value of 10 by 3 is 3.333. So it is recurring. After decimal, 3 is recurring. So the statement, if a real number is rational, then its decimal expansion is terminating. This statement is false. Subquestion 3. If a transversal intersects two parallel lines, then each pair of corresponding angles is equal. So the figure I have drawn here, you can see L and M are two parallel lines, and PQ is the transversal which intersects these two parallel lines, L and M. So whenever transversal intersects two parallel lines, we get corresponding angles. So what are the corresponding angles here? Okay, so this angle and this angle is one pair of corresponding angles, and corresponding angles will be equal in measure. Similarly, this angle and this angle is another pair of corresponding angles which will be equal. Now, what is the converse of this statement? The converse is, if a transversal intersects two lines in such a way that a pair of corresponding angles are equal, then the two lines are parallel. Okay, the converse also is true. Okay, so whenever a transversal, or simply we can say a line, intersects two lines such that corresponding angles are formed, then that means these two lines are parallel to one another. Subquestion 4. If each pair of opposite sides of a quadrilateral is equal, then the quadrilateral is a parallelogram. So the converse will be, if a quadrilateral is a parallelogram, then each pair of opposite sides is equal. So both the statements are true. See here, you can see the diagram of a quadrilateral and a parallelogram. So quadrilateral is a polygon formed by four sides. Okay, even parallelogram is a polygon formed by four sides, but in a parallelogram the opposite sides are equal in length. Okay, this length is equal to this length, and this length is equal to this length. Therefore both the statements are true. That is, if each pair of opposite sides of a quadrilateral is equal, then the quadrilateral is a parallelogram, and if a quadrilateral is a parallelogram, then each pair of opposite sides is equal. So both the statements are true. Subquestion 5. Two triangles are congruent, then their corresponding angles are equal. The converse of this statement will be, if the corresponding angles of two triangles are equal, then they are congruent. To answer this, we need to know what are congruent triangles and similar triangles. Okay, so two triangles are congruent only if their corresponding angles are equal and also the corresponding sides are equal. Okay, and two triangles are said to be similar if their corresponding angles are equal. The sides may not may be equal or may not be equal, okay, and all congruent triangles are similar triangles, but not all similar triangles are congruent, okay. So therefore the statement that if the corresponding angles in two triangles are equal, they are congruent is false, okay. If the corresponding angles are equal, the triangles may be similar but not necessary that they are congruent. Next is exercise A 1.5. Write the converse of the following statements. If it is hot in Tokyo, then Sharon sweats a lot. So the converse will be, if Sharon sweats a lot, then it is hot in Tokyo. Second sub question, if Shalini is hungry, then her stomach grumbles. So the converse will be, if Shalini's stomach grumbles, then Shalini is hungry. Third statement is, if Jaswant has a scholarship, then she can get a degree. So the converse will be, if Jaswant can get a degree, then Jaswant has a scholarship. The fourth sub question is, if a plant has flower, then it is alive. So the converse will be, if a plant is alive, then the plant has flowers. Fifth sub question is, if an animal is a cat, then it has a tail. So the converse will be, if an animal has a tail, then the animal is a cat. Here, while stating the converse of the statement, we are not bothered about the truthfulness of the converse. For example, in the last sub question, if an animal is a cat, then it has a tail. The converse of this is, if an animal has a tail, then it is a cat. So it's not necessary that all animal which has a tail is a cat, right? Therefore this converse is maybe false also, okay. Similarly, in the first sub question, if it is hot in Tokyo, then Sharon sweats a lot. The converse is, if Sharon sweats a lot, then it is hot in Tokyo. So here also it's not necessary that whenever Sharon sweats a lot, it's hot in Tokyo. The converse need not be true, and we are not bothered about that also. Our job is just to give a converse of the statement. Exercise A 1.5, question number 2. Write the converse of the following statements. Also decide in each case whether the converse is true or false. First sub question, if triangle ABC is isosceles, then its base angles are equal. So the converse is, if the base angles of a triangle ABC are equal, then it is isosceles. So and this statement is true. See, you can see this diagram here in this triangle ABC. Angle B and angle C are base angles, and angle B is equal to angle C. That means base angles are equal. So whenever the base angles are equal, then the sides AB and AC as shown here will be equal. Therefore whenever base angles are equal, the given triangle is an isosceles triangle, and hence the converse is true. Sub question 2, if an integer is odd, then its square is an odd integer. So the converse of this statement is, if the square of an integer is odd, then the integer is odd. So and this statement also is true. Here you can see 9. So 3 square is equal to 9. 9 is an odd number. Therefore 3 also is an odd number, okay. And 5 square is equal to 25. 25 is an odd number. Therefore 5 also is an odd number. Therefore if the square of an integer is odd, then the integer is odd is a true statement. Sub question 3, if x square is equal to 1, then x is equal to 1. So the converse will be, if x is equal to 1, then x square is equal to 1, okay. So now take this equation, x is equal to 1. When we square both the sides, we get in the left hand side x into x, x square. In the right hand side, 1 into 1 is 1 square, which is equal to 1. Therefore x square is equal to 1. So therefore this statement, this converse is true. Sub question 4, if ABCD is a parallelogram, then AC and BD bisect each other. So the converse of this statement is, if AC and BD bisect each other, then ABCD is a parallelogram. Okay, so in any parallelogram the diagonal bisect each other. Okay, if ABCD is a parallelogram, then AC and BD bisect each other. That means if O is the point of intersection, then AO is equal to OC, then and BO is equal to OD. That way it is. Okay, and also if you draw any two lines which intersect each other and at the same time if it is bisecting one another, and if we join all the end points this way, then we'll get a parallelogram. Okay, therefore this statement is true. If AC and BD bisect each other, then ABCD is a parallelogram. Sub question 5, if A, B and C are whole numbers, then A plus B plus C in the bracket is equal to A plus B in the bracket plus C. So the converse will be, if A plus B plus C in the bracket is equal to A plus B in the bracket plus C, then A, B and C are whole numbers. So this is not necessarily true. Okay, for example, now what are whole numbers actually? So whole numbers are 0, 1, 2, 3, 4, 5 like this, and integers are positive numbers, negative numbers and 0. Okay, now if I take A is equal to 1, B is equal to 2, and if I take C is equal to minus 3, okay, I'll take integers, okay, 1, 2 and minus 3, and if I substitute, I'll get left hand side is equal to right hand side. So not necessary that if this condition is satisfied, not necessary that the given ABC are whole numbers only, they can be integers also. Okay, so therefore we can consider this converse to be false. Sub question 6, if x and y are two odd numbers, then x plus y is an even number. So the converse of the statement will be, if x plus y is an even number, then x and y are odd numbers. Okay, now consider this example, 3 plus 5 is equal to 8. 8 is an even number, but 3 and 5 are odd numbers. It looks like this statement is true, but consider another example, 2 plus 4 is equal to 6. 6 is an even number, and 2 and 4 also are even numbers, they are not odd numbers. Okay, so this statement is not always true. Whenever x plus y is an even number, it's not always true that x and y are odd numbers. X and y can be even numbers also. So since this is not always true, we'll consider this statement as false statement. Sub question 7, if vertices of a parallelogram lie on a circle, then it is a rectangle. Now consider this diagram here. Take any circle and take any 4 points on the circumference of the circle and join all those 4 points. You will get a quadrilateral, and if the opposite sides are parallel to one another, then you get a parallelogram, and if the opposite sides are parallel and also equal in length, then it will be a rectangle. For example, here this length is equal to this length and these two sides are parallel to one another, and this length is equal to this length and these two sides are parallel to one another. In such a situation, this will be a rectangle. So the given statement is a true statement. Now coming to the converse of the statement, the converse of the statement says, if a parallelogram is a rectangle, okay, if a parallelogram is a rectangle, its vertices lie on a circle. Okay, now again consider this same figure. Now first you draw any rectangle, and this is the diagonal. Okay, see where the cursor is going, diagonals will be like this. Now keeping this diagonal as a diameter, if we draw a circle, then the circle passes through all the 4 corners of the rectangle. Okay, so and hence this statement also is true, that is the converse. If a parallelogram is a rectangle, then its vertices lie on a circle is a true statement. In all these examples, if you just give the converse of the statement and say whether it is true or false, it is just sufficient. There's no need to give all this explanation, but I have given all this explanation just for your understanding. The next topic in this chapter is proof by contradiction. So this method we use to prove a given statement, okay, and this is a very powerful tool in mathematics. And here you can read, we have already used this method in chapter 1 to establish the irrationality of several numbers, and also in other chapters to prove some theorems, okay. So chapter 1 means they are referring to real numbers, okay. So in some textbook the chapter number is different. So in this is Karnataka state textbook, here the real number is chapter 8, okay, but in many textbooks the chapter number could be real number could be chapter number 1, okay. So whatever the chapter number may be, but all state schools who have implemented national education policy will have same school syllabus and content. So even the chapter number is different, you don't have to worry, the content will be same. In this method what we will do is, to prove a given statement, we don't try to prove a given statement to be true. Instead we will try to prove that the given statement is false, and if we don't succeed to prove that the given statement is false, that means the given statement is true, okay. So what we do is, to prove a given statement P to be true, what we do is we assume P to be false, okay, and we will try to prove that P is false, okay. What we'll do is we'll perform deductive reasoning to prove P is false. And while proving, if a contradiction arises, then it is because that our assumption that P is false is not correct, therefore P must be true. This is how we prove a given statement to be true, and this method is called as proof by contradiction. Next is an example in the textbook. Example 15. The product of non-zero rational number and an irrational number is an irrational number. So we should prove this statement using the method of proof of contradiction. The answer is already given here, you can go through it, and if you write this answer in the exam, it's not necessary to put all these comments, okay, but these statements are very necessary to prove it. So the same question I'll try to prove in my own words here, okay. Now I should prove that non-zero rational number into irrational number is an irrational number, okay. Now I'll take R is equal to m by n, or non-zero rational number. So non-zero rational number means m and n are integers, and both m not equal to 0 and n also not equal to 0, okay. And also I'll take x to be a irrational number, okay. So these are the two hypotheses I am making, okay. Now I should prove that R into x, R is an rational number, x is an irrational number, so R into x is an irrational number. I should prove that, okay. Now what I will do is, instead of proving R into x as an irrational number, I will assume that R into x is a rational number, okay. Let us assume R into x is a rational number, okay. I will assume this as a rational number, therefore R into x is equal to P by Q, let us say. So rational number means it is in the form of P by Q, where both P and Q are integers and Q not equal to 0. Now what is R? According to the hypothesis, R is equal to m by n. So substitute that m by n into x is equal to P by Q. So when we cross multiply, we get x is equal to P into n by Q into m. So what is P? P is an integer, right? What is n? N also is an integer. And what is q? Q also is an integer. And what is m? M also is an integer. So q and m both are not equal to 0. Okay. So in the numerator, what is an integer in what is integer into integer? Integer into integer is an integer only. Okay. And what is here also in the denominator, integer into integer is an integer only. Okay. Therefore x is equal to integer by integer. Integer by integer is a rational number actually. Okay, this is a rational number. But according to our hypothesis says that x is an irrational number. But here we are getting x to be a rational number. So there is a contradiction. Okay, I am writing here. But the hypothesis says that x is a irrational number. So and there is a contradiction now. Okay, this contradiction arises because our assumption, what did we assume? We assumed that x into r is a rational number. Okay, we assumed x into r is a rational number. Therefore our assumption itself is wrong. So this contradiction arises because our assumption that r into x is a rational number is not correct. Our assumption itself is not correct. Therefore we can conclude that r into x is an irrational number. So this is the proof. See, this is how we prove. We were supposed to prove r into x is an irrational number, but we assumed that r into x is an rational number, and we tried to prove it, but we were not successful. Therefore r into x should be an irrational number only. So this is how we prove in the method of contradiction. The next example in this chapter is example 11. So this example 11 is already proved in the textbook. If you go some pages back, this example is proved by the method of proof by exhaustion. So the same example we are going to prove now by the method of proof by contradiction. Okay, so example 11 says that every prime number greater than 3 is of the form of 6n plus 1 or 6n plus 5, where n is some integer. Okay, so I'll write the hypothesis. So hypothesis is that P is a prime number greater than 3. Now I should prove that P is in the form of 6n plus 1 or 6n plus 5, but instead I'll assume that P is not in the form of 6n plus 1 or 6n plus 5. Okay, so proof, let P is not in the form of 6n plus 1 or 6n plus 5. Okay, now I'll divide P by 6. If I divide P by 6, I'll get remainder 0, or I'll get remainder 1, or I'll get remainder 2 or 3 or 4 or 5 only I'll get. Let quotient be n. Okay, therefore P is equal to 6 times of n, or P is equal to 6 times of n plus 1, or P is equal to 6 times of n plus 2, or P is equal to 6 times of n plus 3, or P is equal to 6 times of n plus 4, or P is equal to 6 times of n plus 5. So this is according to Euclid's division lemma. Okay. Now we have assumed that P is not in the form of 6n plus 1 and P is not in the form of 6n plus 5. Okay. Therefore P is equal to 6n. Now P is equal to 6n or P is equal to 6n plus 2. Okay, P is equal to 6n or P is equal to 6n plus 2 or P is equal to 6n plus 3 or P is equal to 6n plus 4. Okay. So if P is equal to 6n, this I can write 2 into 3 into n. That means 2 is a factor of P and 3 is a factor of P. So this implies P is not a prime number. So now there is a contradiction. Hypothesis says that P is a prime number, but here we are getting P is not a prime number. Similarly, if P is equal to 6n plus 2, again here also I can take 2 common factor, I'll be left with 3n plus 1. So again 2 is a factor of P. That means P is not a prime number. Okay. If I take P is equal to 6n plus 3, here I can take 3 common factor and I am left with 2n plus 1. So again 3 is a factor of P. So this means P is not a prime number. Again if I take P is equal to 6n plus 1, here also if I take 2 common factor, I am left with 3n plus 2. Again here 2 is a factor of P. Again this implies that P is not a prime number, but according to hypothesis P is a prime number which is greater than 3. Okay. This contradicts the hypothesis which says that P is a prime number. Okay. Why this contradiction arise? Okay. This contradiction arise because of our assumption. So in the proof, in the first line of the proof only, I assume that P is not in the form of 6n plus 1 or 6n plus 5. Okay, that assumption itself is wrong. This contradiction arises because our assumption that P is not in the form of 6n plus 1 or 6n plus 5 is not correct. Therefore, we can conclude that P is in the form of 6n plus 1 or 6n plus 5, and that completes the proof. I hope things are clear for you in this problem. See here and here, what is a prime number? Prime number is a number whose factor is just 1 and itself only. But here we can see we are getting 2 is a factor of P and 3 is a factor of P. That's why P is not a prime number. Here also 2 is a factor of P. Okay. If there is any number which is a factor of the given number other than 1 and itself, then that number is not a prime number. Okay. That's why in all these cases we get that P is not a prime number. Okay. But actually, according to hypothesis, P is a prime number, and that's how we got this proof. You can use your own words and prove this problem. Okay, in the textbook you can see there are many comments here. Okay, writing all these comments are time consuming, so you can avoid writing comments in the exam, and you can just state statements like this, or as I have done here, or you can use your own words and sentences and prove it in your own style. That's also fine. Next in the textbook is a theorem A 1.2. Out of all the line segments drawn from a point to a point of a line passing through the point, the smallest is the perpendicular to the line. Okay, this theorem you have already studied in your previous classes. Okay, now consider this line xy. The xy is a straight line and P is an external point. From point P, I will draw lines like this: AM, A1, A2, all this, and many more lines. Only 3 lines I have shown, but there are a lot of lines. Okay, PA, PM, PA1, PA2, like this. Okay, now the smallest line is PM. Okay, and I should prove that the smallest line is perpendicular to line xy. That's the meaning of this theorem. Okay, the smallest line is the perpendicular to this line. So to prove this, so first I have written the hypothesis. You can see xy is a straight line. Okay, P is an external point. P is an external point. Okay, external point means this line is not passing through this point. That's the meaning. Okay, P is an external point. Then PM, PA1, PA2, etc. are line segments drawn from P to line xy, and PM is the smallest line. Now I am supposed to prove that PM is perpendicular to the line xy. So I'll start the proof. So instead of proving that PM is perpendicular, I'll assume that PM is not perpendicular. Okay, let PM not be perpendicular to xy. I'll assume that PM is not perpendicular to xy. Now I'll make some construction. Draw PN perpendicular to xy. So from point P, I'll draw one line perpendicular to xy. So perpendicular means this angle will be 90 degree. Okay, now triangle PMN is a right angled triangle. Okay, right angled triangle, right angled at N. Okay, now in any right angled triangle, the hypotenuse is the greatest side, right? Okay, that is PM is greater than PN. Why? PM is the hypotenuse. Okay, you can see in the diagram. Okay, according to the construction, PM is greater than PN. That means PN is smaller than PM. But according to hypothesis, PM is the smallest side. Therefore, there is a contradiction here. This contradicts the hypothesis. Which says that PM is the smallest side. Okay, why this contradiction arise? This contradiction arise because of our assumption that, so in the proof, in the first line of the proof, you can see we assume that PM is not perpendicular to xy. Okay, that assumption itself is wrong. This contradiction arises because of our assumption that PM is not perpendicular to xy is not correct. Our assumption itself is not correct. Is not correct. Therefore, PM is perpendicular to xy, and that completes the proof. I've used my own words to prove this, and I've made it as simple as possible. And here you can see in the textbook there are many comments here, so writing all these comments will be tedious and time consuming, and you can just avoid writing comments in the exam, and you can just give statements like this, okay, one by one, okay, or in the way I have used here, okay. You can use your own style and give explanation, that's not an issue. And the next here is exercise problems. Exercise A 1.6, question number 1. Suppose A plus B is equal to C plus D and A is less than C. Use proof by contradiction to show that B is greater than D. So there are two hypotheses, that is A plus B is equal to C plus D and A less than C. Okay, these are the two hypotheses given. So hypothesis means statements which are true. So these two are true. So now I should prove that B is greater than D. Okay, now proof. So I should prove that B is greater than D. Instead of that, I'll assume that B is less than D. Okay, let B be less than D. Okay, this I'll mark as 1, this I'll mark as 2. Okay, now I'll add 1 and 2. Equation 1 plus equation 2 gives, so what is 1? A is less than C. What is 2? B is less than D. So if I add these two, in the middle the less than symbol B will be as it is. In the left hand side I'll get A plus B, in the right hand side I'll get C plus D. Okay, now this I'll mark as 3. Okay, but equation 3 is contradicting the hypothesis. Okay, hypothesis says that A plus B is equal to C plus D. Okay, this contradicts the hypothesis that A plus B is equal to C plus D. Okay, why this contradiction arose? Okay, this contradiction arises because our assumption that B is less than D. So in equation 2 we assume that B is less than D. So that assumption itself is wrong, because our assumption that B is less than D is not correct. Therefore B must be greater than D, and that completes the proof. Exercise A 1.6, question number 2. Let R be a rational number and X be an irrational number. Use proof by contradiction to show that R plus X is a irrational number. Many similar problems like this are there in chapter real numbers. You can go through that chapter. Now here R is a rational number. Okay, any rational number is given in the form of P by Q, where both P and Q are integers and Q not equal to 0. Okay, and also given that X is a irrational number. Okay, these are the two hypotheses given. What are hypotheses? Hypotheses are statements which are either true or false. So here the given hypothesis is supposed to be true. Now I should prove that R plus X is a irrational number. Okay, now what is an example of a irrational number? Okay, root 2, root 5, root 7, all these are irrational numbers. Okay, now 5 by 2 is a rational number. If I add a irrational number, for example say root 5, and whatever I'll get should be a irrational number, and I'm supposed to prove now. Okay, now proof. So now instead of trying to prove that r plus x is an irrational number, I'll assume that r plus x is a rational number. Okay, I'll contradict and I'll assume that r plus x is a rational number. So r plus x is equal to, so what is r? P by q plus x. Now x means I can take as x by 1, so p by q, so LCM of q and 1 is q, so p by q plus x by 1 into q by q, multiply and divide by q. So this is equal to p by q plus x into q is xq, and 1 into q is q. Now again here I can take q common in the denominator, so please p plus x into q I'll get. Now what is x into q? X is an irrational number, q is an integer. Okay, irrational number into integer is an irrational number only. Okay, so here p is an integer plus x into q is irrational number. Okay, divided by q. Now here q is an integer and p also is an integer. Okay, so in the numerator it is integer plus irrational number. Integer plus irrational number gives an irrational number only. Okay, divided by integer. Now again irrational number divided by an integer is an irrational number only. So r plus x is a irrational number, so this I'll mark as B. Okay, so and here first statement in the proof I mark as A. Now we can see first A, according to A r plus x is a rational number, but according to B r plus x is an irrational number, so there is a contradiction. Okay, this contradicts our assumption that r plus x is a rational number. Okay, therefore r plus x is a irrational number. So here x into q is an irrational number. Okay, if you want to give me an example, now root 2 is an irrational number. If you multiply by any integer, like for example say 3 root 3 is an irrational number. Okay, and again here irrational p integer plus irrational number. Okay, now for example if you take 5 plus root 7 is an irrational number, 5 is an integer, 5 plus root 7 is an irrational number. Okay, and that completes this proof, and you can refer chapter real numbers. Many such similar problems are there in that chapter. Exercise A 1.6, question number 3. Use proof by contradiction to prove that if for an integer a square is even, then so is a. So here given a is even and a square, sorry, a is integer and a square is even. Okay, these are the two hypotheses given. Okay, so the question is, if a square is even, then prove that a is, sorry, if a if a square is even, then prove that a is also even. Okay, that's the question. So proof goes like this. So there is a hint also in the question. Assume a is not even, that is, it is in the form of 2n plus 1 for some integer n, and then proceed. So we'll assume that a square is even and a is odd. Let a square is even and a is odd. Okay, I'll mark this as a. Okay, odd number is given by 2n plus 1 for some value of n which is an integer. Okay, therefore a is equal to 2n plus 1. Okay, give any value of n is an integer, so n may be 0, 1, 2, 3 or minus 1, minus 2, minus 3, anything. If we give value for n, then a we get odd number only. Okay, therefore now a square is equal to 2n plus 1 the whole square. So this is equal to, now expand, 2n the whole square plus 1 the whole square plus 2 into n, 2 into 2n into 1. So I am using the formula a plus b the whole square is equal to a square plus b square plus 2ab. Okay, so now this is equal to 2n the whole square is 4n square plus 1 square is 1 plus 2 2 is 4, 4 1 is 4, 4n I'll get. So I'll simplify 4n square plus 4n plus 1. So here I'll get, if I take 2n common, I'll get to 2n plus 1 plus 1. Now again you can see 2n plus 1 is an odd number and 2n is an even number. Okay, where n is an integer. Okay, so give n may be 0, 1, 2, 3, 4, 5, 6 like this, or n can be 0, minus 1, minus 2 like this also. It can be negative number, positive number or 0. So whenever n takes any value, we get 2n to be even number and we get 2n plus 1 to be a odd number. Now what is even number into odd number? Even number into odd number is an even number only. Okay, so this is an even number. Okay, this whole from here till here, it is even number, and plus this 1 as it is. So even number, if you add 1 to an even number, you get odd number. Okay, so now there is a contradiction. I'll mark this B. This is a square. A square I am getting odd number. This contradicts our hypothesis which says that, so according to hypothesis, a square is even, you can see there. Okay, now why this contradiction arise? This contradiction arise because of our assumption. What did we assume? So in A you can see we assumed that A is an odd number. So this contradiction arises because of our assumption that A is an odd number, which is not correct. Okay, therefore A is an even number. A is an even number if A square is even. And that completes the proof. Exercise A 1.6, question number 4. Use proof by contradiction to prove that if for an integer a square is divisible by 3, then a is divisible by 3. So here given that a is an integer and a square is divisible by 3. Okay, these are the two hypotheses given in this question. So hypotheses are nothing but statements which are either true or false. So here the statements, the hypothesis is assumed to be true. So a is an integer and a square is divisible by 3. We should prove that a is also divisible by 3. That's the question. Okay, so proof. So here let a square be divisible by 3 and a not divisible by 3. So I am supposed to prove that a is divisible by 3, but instead I will assume that a is not divisible by 3 and I'll go ahead. Okay, I'll mark this as a. Now if a is not divisible by 3, what is the result? Suppose if you divide a by 3, if a is not perfectly divisible, then we get remainder 1 or 2. Okay, we will never get remainder 0. If remainder is 0, that means a is divisible by 3. Okay, so let us say that quotient is k. Okay, therefore since we have assumed a not divisible by 3, we can write a as 3k plus 1 or 3k plus 2. Okay, 3k plus 1 or 3k plus 2. Now consider 3k plus 1 or 3k plus 2 only, because remainder is just 1 or 2. That's why 3k plus 1 or 3k plus 2 only. 3k plus 0 is not there because we won't get 0 if a is not divisible by 3. Okay, now consider a square by 3. Now out of these two, any one I'll take. Okay, I'll take first one only. So a square by 3 is 3k plus 1 the whole square by 3. So this is equal to, now expand using the formula, a square plus b square is a plus b the whole square is a square plus b square plus 2ab, right? So expand the numerator. Now the numerator is 3k the whole square plus 1 square plus 2 into 3k into 1 by 3. So now this is equal to 3k the whole square is 9k square plus 1 square is 1 plus 2 3s are 6, 6 1s are 6, 6k by 3. So this is equal to 9k square plus 6k plus 1 by 3. I am just rearranging it. Okay, now this I can also write as, in the first two terms I can take 3k common factor, so I'm left with 3k plus 2 plus 1 by 3. So this is equal to 3k into 3k plus 2 by 3 plus 1 by 3. So just split the terms now. So this is nothing but a square by 3. So here 3 will get cancelled. So a square by 3 is equal to k into 3k plus 2 plus 1 by 3. So now here you can see k into 3k plus 2 is an integer, okay, and this is a 1 by 3 is a fraction. So what it means is a square is not divisible by 3. If it is divisible by 3, we won't get a fraction here, okay. So this implies that a square is not divisible by 3, okay, but this contradicts the hypothesis. According to the hypothesis, a square is divisible by 3. So this contradicts the hypothesis which says that a square is divisible by 3. And why this contradiction came now? Why it came now? Because we assumed that a is not divisible by 3. So in the proof, check this a. So in a, we assume that a is not divisible by 3. That's why this contradiction is coming here, okay. So this contradiction arises because our assumption that a is not divisible by 3 is not correct. Therefore a must be divisible by 3. Therefore a is divisible by 3, and that completes the proof. Exercise A 1.6, question number 5. Use proof by contradiction to show that there is no value of n for which 6 power of n ends with a digit 0. So I should prove that 6 power of n does not end with a digit 0. So instead of that, I'll contradict the statement, and I'll assume that 6 power of n ends with a digit 0, okay. Any number which ends with 0 is divisible by 5. For example, 100 is divisible by 5, 10 is divisible by 5, 230 is divisible by 5, okay. Therefore 6 power of n is divisible by 5, okay. So divisible by 5 means if I divide, I should get remainder 0, okay. Remainder should be 0. Let us say k is the quotient, okay. Therefore I can write 6 power of n by 5 is equal to k. Now k is a positive integer, okay. Always quotient will be positive integer. So here we'll assume n is positive integer only, okay. Now 6 power of n I can write as 2 into 3 to the power of n, okay, and 5 is equal to k. Now again, the left hand side I can write as 2 power of n into 3 power of n by 5 is equal to k. Now this is equal to 2 into 2 into 2 up till n times into 3 into 3 into 3 up till n times by 5 is equal to k. Now k is a positive integer, okay. So right hand side is a positive integer. What about the left hand side? Left hand side is a decimal, okay. Left hand side is decimal. Why it is decimal? Because in the numerator and the denominator there is no common factor at all. That's why left hand side will be decimal, and the right hand side we are getting a positive integer. Therefore the left hand side is not equal to right hand side. Now there is a contradiction, okay. Left hand side should be equal to right hand side, but here we are not getting like that. There is a contradiction. Both should be decimal or both should be positive integer, okay. Left hand side is a decimal because no common factor between numerator and denominator, okay. And right hand side is a positive integer. Therefore LHS is not equal to RHS. So why this contradiction arise? This contradiction arise because of our assumption that 6 power of n ends with a digit 0. So in the first line of the proof only we assume that 6 power of n ends with a digit 0, okay. That assumption itself is wrong. Therefore 6 power of n does not end with digit 0 for any value of n, okay. And that completes the proof. Exercise A 1.6, question number 6. Prove by contradiction that two distinct lines in a plane cannot intersect in more than one point. So according to definition of distinct lines, it means straight lines which intersect at only one point or which is parallel, okay, like this, okay. If two lines are parallel, then they are distinct lines, and if two straight lines, if they intersect like this, they are also distinct lines, okay. Now what is a plane? Plane means it is a xy plane. So this is the origin, this is x axis and this is y axis. Now consider two lines, line M and L, okay. These are the two lines. Let they intersect at point O. Now I should prove that these two lines, these two straight lines intersect at only one point. They won't intersect at another point, okay. Now on the contrary, okay, let me first write the hypothesis. L and M are straight lines, okay, and L and M intersect at point O. I should prove that these two lines will not intersect at another point apart from point O, okay. So on the contrary, I'll contradict that and I'll assume that L and M intersect at another point apart from O. Okay, let L and M intersect at another point apart from point O. So like this is just an assumption. This is line L and this is line M. They are intersecting at 2 points like this. I'm just assuming. Okay, this O and this is some other point. Okay, but now there is a contradiction. So there is a axiom which says that between any two points only one straight line can pass. Okay, suppose if there are 2 points P and Q, only one straight line can pass through those 2 points. This contradicts the axiom that only one straight line can pass through 2 distinct points. Okay, between 2 distinct points only one straight line can pass through. Okay, if there are more than 2 lines passing through that points, means those 2 lines are not straight lines. Okay, now I assume that L and M intersect at point O, but according to this axiom, between 2 points only one line can pass through. Okay, therefore our assumption itself is wrong. Therefore our assumption that the lines L and M intersect at 2 points is not correct. Okay, if L and M has to intersect at 2 points, means one should be curved line or both should be curved lines. Okay, but between 2 points only one straight line can pass through. Okay, therefore our assumption is wrong, and therefore L and M does not intersect at more than 2 points, and that completes the proof. Summary of this chapter: in this appendix you have studied the following points: different ingredients of a proof and other related concepts learnt in class 9. So ingredients of a proof are nothing but the statements. So we'll make a series of statements which are either true or false, and we'll prove the given statement. And the negation of a statement we have learnt, the converse of a statement also we have learnt, and proof by contradiction also. In one example we learnt how to prove by the method of proof by exhaustion also.